Okay, let's delve into chemical reactions a bit deeper. And here is an equation for photosynthesis. And I've broken it down a little bit differently from the traditional reactants arrow products just to show things just slightly differently. Carbon dioxide plus water makes sugar and oxygen using sunlight as an energy source that this requires. This is a chemical reaction, and this is just an exceedingly important chemical reaction that really is unique in all the reactions we may want to look at. Here's how I might write it in a more chemistry style way. And note that when reactions are shown, sometimes we show the state of each of the reactants and products, and sometimes it's written just more colloquially without putting all of that down. It's all okay. I think that this could be written showing carbon dioxide gas, liquid water, solid sugar, gaseous oxygen, but those are really just states that we know these are going to be in from a practical sense. So it's really just kind of not all that important. And for this class, focus on the big picture of chemical reactions. And that is on the left side, we have reactants. These are the materials, the ingredients. We cannot have photosynthesis function without water and carbon dioxide. If you've ever been a gardener and you put your plants out there, they got plenty of CO2, that's in the atmosphere. They can be in plenty of sun, but if you don't water them, they will not grow, right? Because photosynthesis drives plant growth. Without water, it's just not going to happen. The products are the ending materials, and this is sugar and oxygen. And notably here, this sugar, this is what plants use for food. So this is the growth, that sugar is like a carbohydrate. It can be turned into calories, which can be used for energy, for just so many processes. And in that regard, this is kind of like the opposite of the fuel consuming reaction we saw before. Sugar is like biological fuel. It may not be what exactly we carry the energy around in, but it's a really common starting material from which organisms derive energy. And organisms need energy to do the huge range of functions that are necessary for life. When we look at this, is this endothermic or exothermic? And here, I think when you're thinking of any reaction, it's always good to think of your own sensibility first. What do you know about photosynthesis? Have you seen photosynthesis before? Starting there and thinking, oh, photosynthesis, does this create raw heat or energy as it's functioning? Or does it require raw heat or energy in order to function? That's a really good example of whether the good thing that'll guide you towards endothermic or exothermic. So go ahead, pause here, and see if you can answer that correctly. All right, photosynthesis, this is endothermic. The energy input is from the sunlight. And I know we talked about sugar as like an energy source, but it's not pure energy. It's something that the energy that this reaction is requiring is being directed toward. It's being directed to be stored in the sugar, which could be, sitting on your counter. It's really the same sugar. This can be used in an organism that exists and uses it now, or it could grow in the plant and be cut down and used later to make Coca-Cola or something like that. Sugarcane's a plant. And again, the ingredients are carbon dioxide and water. Using sunlight creates sugar and oxygen. And again, now that we've sort of finished unpacking this chemical reaction, let's think about just how special photosynthesis is. It takes in carbon dioxide, something that there's too much of in the environment right now and is hypothesized and really concluded by the scientific community to be causing negative impacts on the climate. Water is, not always available in all parts of the world, but in a lot of places we have challenges with too much water. We have floods every so often, in Kentucky and in other places, and plants can gobble up this water and make the land better. So it's two ingredients that we really don't want, and plants will turn them into sugar. Great, we like sugar, that's food, and oxygen. Oxygen, the air we breathe. It's the reason why life has become so sophisticated, is that we have the ability to breathe oxygen in the air. That you'll definitely look at a lot more if you continue on with molecular biology, biochemistry, or just a lot of places in the field. Oxygen in the air and an ability to breathe in, a lot of it is related to the highest order of life forming on planet Earth. Okay, what about reversible reactions? So what we looked at before, this is photosynthesis, and it's really not reversible. We can't just take sugar and oxygen and put out sunlight, water, and carbon dioxide. It just doesn't work like that. Some reactions are non-reversible. They really just go one way, and we're not able to reverse them and go backward. But what about blood pH when a patient hypoventilates? So this is the reaction that occurs. So carbon dioxide with water is going to make H plus and HCO3 minus. And this we're not looking into a whole lot right now. H plus we're going to learn next chapter is a unit of acidity, but the idea here is that this is an equilibrium reaction. It's a reversible reaction that carbon dioxide, water, acidity, and this bicarbonate polyatomic ion are related through this reaction where it can be pushed more to the right if needed or pushed more to the left if needed. The reaction can go forward or backward. We call this a reversible reaction, and that's why we call it reversible. And note that in the text and materials and all out there, we'll often see this shown with H2CO3 in the middle. This is technically more accurate, but I think does blur the idea of a strictly reversible reaction, the products and the endpoint, the reactants and the products, and so I think that using the top version with just one double-sided arrow is good. And again, note that that arrow in the middle is not a single-sided arrow like we saw with photosynthesis, but is this double with one side on each of the arrows, equilibrium arrow. Okay, so equilibrium. This is what's going to come up with reversible reactions all the time because the reaction can go forward, the reaction can go back. Let's think about this as people going up an escalator and people coming down an escalator. They are the reverse process, right? Going up an escalator is someone goes from the bottom floor to the top floor. Coming down is the top floor to the bottom floor. If someone goes up, that's taking one reactant on the left and turning into a product on the right. People coming down is reversing it. So hopefully you can see how this is similar. If the same number go up and down, so we're watching and 3 people are going up, 3 people are going down, and then 5 people going up, 5 people going down, and if it's constantly the same number of people, the total number of people on each floor stays the same. And that's equilibrium, that we can have a reversible reaction where both reactions are occurring, but they occur at the same rate. So the big picture, the concentrations, the pH of blood doesn't change. And I like to think of this as jugglers, right? They're tossing pins back and forth. And if we watch for a long time, it almost looks as if the pins are staying in place, right? They're going back and forth, but there's 2 in their hands, 4 in the air pretty much the whole time. However, the equilibrium reaction is happening. The forward reaction from left to right is happening at the same speed as the reverse reaction from right to left. And that is a good example of chemical reactions that are reversible in a state of equilibrium, which is exceedingly important to know. We'll look at how reactions adjust where they keep their equilibrium based on external conditions in the next video.